Hello, my name is Aurélien, and in this short video I would like to talk about the results from our paper towards optimal multi-level checkpointing. Okay, so first of all, what is checkpointing and why is it needed? Consider an application that executes on a large-scale platform with millions of processing cores. With so many components working together, errors are frequent. The standard solution to cope with this kind of failures is periodic checkpoint rollback and recovery. The execution of the application is divided into equal length chunks of work of size W. After each successful execution, the data is saved to some stable storage with cost C. This is a checkpoint. When an error strikes, the execution is interrupted and all the work done so far is lost. But thanks to the checkpoint, the application doesn't have to restart from scratch. Instead, the application can roll back to the last checkpoint and simply resume its execution from there. Now the question is, what is the optimal checkpointing interval? If the checkpoint interval is too small, we waste too much time performing checkpoints. But if the checkpoint interval is too large, then we lose too much time due to failures. Because for each error, we have to roll back further and re-execute more on average. Young and Daly have proposed a universal solution to this problem. They have derived a first-order approximation of the optimal checkpointing interval and its associated execution overhead. Note that the overhead is simply the square root of 2 lambda c, where c is the cost of the checkpoint and lambda is the error rate of the platform. This formula is simple and applicable to a wide range of applications. However, it is only useful for a single level of checkpoint. In this paper, we investigate the use of multiple technologies to cope with different types of failures. This includes, for example, checkpoints in the local memory, or SSD, checkpoints on a partner node, the use of Reed-Solomon coding, or checkpoints in the parallel file system. Checkpoints in the local memory are cheaper than checkpoints in the parallel file system, but if the node on which the local checkpoint was made is lost, the checkpoint becomes unusable. In this work, we consider synchronized checkpointing. Standard checkpoints in the parallel file system are mandatory, but intermediate, cheaper, periodic checkpoints can be inserted. Consider this example with 3 levels of checkpoints. Level 1 is a local memory, level 2 is a partner copy, and level 3 is a parallel file system. The exact solution is unknown, but under first-order approximation, it is possible to minimize the overhead and derive the optimal checkpoint interval. Note the similarity with the results of Young and Daly. Because different sets of checkpoints can be used, we also provide in this paper a dynamic programming algorithm to choose the optimal set of levels. The main result of this paper is the generalization of the formula for the optimal checkpointing interval to an arbitrary number of checkpoint levels. The proof, which is available in the paper, is quite technical, but ultimately we were able to derive both the optimal checkpointing interval, the optimal number of checkpoints at intermediate levels, and the optimal associated execution overhead. It is striking that the optimal overhead for multi-level checkpointing turns out to be the sum of the square roots for each level, exactly as in Young and Daly's original formula. So, in summary, checkpointing is a de facto standard technique for HPC resilience at scale. Multi-level checkpointing is mandatory to minimize overhead. Young and Daly have proposed a universal solution for a single level of checkpoint. And in this paper, we have extended this result to an arbitrary number of levels. Thank you for watching.